Okay, good morning, everyone on the West Coast, and good afternoon, the Midwest and East Coast. Today, we've got a great presentation on profiling tools, in particular on Expanse, I believe. Bob Sinkovitz and Mahidar Tataneni will be giving the presentation, but before we get started, I want to bring everyone's attention to the Exceed Code of Conduct. We try to be on our best behavior, but if we see any behavior that we think is inappropriate, please submit a report to exceed.org/code of conduct. And Exceed is also making an effort to provide training events that foster inclusion and show respect for everyone. But if you see any terminology that you feel is also inappropriate, please let us know at terminology@exceed.org. And with that, I will stop sharing and hand it off to, I believe Bob will be gone first. Is that right?
Yeah, thanks, Jeff. That's correct. So we're going to be, so let me go ahead and share my screen here. Okay, so again, thank you, Jeff, for the introduction. So today we're going to be covering two profiling tools. I'll be kicking things off with Amd Uproof that we're going to be using to understand behavior of the CPUs. And then at the bottom of the hour, I'm going to hand things off to my colleague, Mahidar Tataneni, who will be describing NSIGHT tool for profiling GPU applications. If you look in the chat, I had posted a link to my GitHub repo that has the examples I'll be working with and also these slides. And I'll post this at the end again for those of you who joined a little late. So before we dive in, just a quick, a few words on why you should profile your code. So imagine that you have an application, you're trying to make it run faster. You might think, hey, I'm going to dive in, I'll start optimizing the code. But modern HPC and data-intensive software is often large, comprising many thousands of lines of codes, in some cases even millions of lines of codes. So you don't want to just jump in and start working on the code. You want to profile it, figure out where the code is spending most of its time so that you know where to focus your effort. Sometimes you want to go a little bit deeper and you want to figure out why those portions of the code are taking so much time. So I find in most cases, just knowing which function or routine is used most of the time is really all the information I need. But sometimes you're going to find, particularly with memory-intensive codes, that diving a little bit deeper and understanding why that portion of code is so expensive is really valuable. And we can use the Amd Uproof tool for both of these. So Amd Uproof, this is a proprietary performance analysis tool that works just for AMD hardware. The basic time-based profiling, what we call TBP, is almost as easy to use as gProf. If you're not familiar with gProf, I suggest that you take some time, investigate gProf. It is a universal tool. You'll find it supported everywhere by every major C and Fortran compiler. And it does a great job of the time-based profiling. But as you're going to see, there are things that we can do with uProf that go well beyond what we can do with gProf. Really nothing special you need to do with your application. I'm just going to suggest compiling with the -G flag so you get simple information. Profiling data is going to be available in two formats. uProf is going to generate CSV files, which are human readable and can also be opened as spreadsheets. And it also generates a SQL-like database that can be imported into the Amd Uproof GUI. So in addition to doing the time-based profiling, we can also access the performance counters to investigate things like cache usage, branch prediction, and instruction-based sampling. So the uProf workflow involves 3 steps. In the first step, we're going to run the application and collect the profile data. In the second one, we're then going to process that profile data to aggregate and correlate it and save them in a database or in a CSV file. And then finally, we're going to analyze the results. Let me just step back one slide. I mentioned that the profiling data is available in 2 formats. The CSV file and the database file contain exactly the same information. It's just that the SQLite database could then be imported into the GUI, but there's no advantage to one over the other. So collect is going to be the first step. Profile data is going to be generated using the Amd Uproof CLI bin tool. So CLI stands for Command Line Interface. And we're going to use this to do our sampling. Generally, you're going to use a predefined profile, and I'll show these on the next couple of slides. So you would start off with the Amd Uproof CLI bin command, followed by the keyword collect, followed by the type of sampling you want to do, --config, followed by the predefined profile, -o output, that's going to specify the prefix of the output file, and then finally your executable, in this case a.out, followed by any command line arguments. So this is going to generate either an output.caperf file if you're working on Linux, like on Expanse, or an output.prd file if you're working on Windows. And this file is then going to be used as input to the translate stage. So I'm not going to go through all of these, but just to show you that there are a bunch of different predefined profiles. This is taken from the Amd Uproof user guide. The one that we're going to be using most often, again, is the time-based sampling, and you can use this to identify where the programs are spending time. You can look at overall performance. You can investigate branching behavior. Data access, this is the one that you're probably going to use most after time-based profiling. This gives you some insight into data access operations, such as cache misses. You'll notice that for the second, third, and fourth predefined profile, we have at the bottom some text that says PMU events, followed by some cryptic looking codes. PMU is just the performance monitor unit, and PMC refers to a specific performance monitoring counter. So what these predefined profiles do is they'll collect together multiple counters that kind of naturally go together. So for example, if we go down to data access, we see that we have these 6 different events, and these are going to correspond to, say, L1 cache misses, L2 cache misses, TLB misses, and so forth. We have a few other predefined profiles, to look at memory access in a little bit different way, instruction-based sampling. Again, most of these I haven't really experimented with. I've been focusing on the time-based sampling and the data access sampling. Yeah, and yeah, to answer the questions, no, uProf is only for AMD hardware. Okay, oops, sorry. But moving on. So right now we do not have uProf installed and available for general use on Expanse. It's a little bit more difficult than a typical install. It requires a certain level of root access since we're tapping into the performance counters. You'll find though that when you start using uProf, that there are certain predefined profiles that you're not going to be allowed to use. And this is based on a setting for something called the perf event paranoid parameter. So don't have time to get into the details here, but once we start providing access to the performance counters, it opens up some potential security risks. And if you're really interested, we have a couple of links here on Stack Exchange and Stack Overflow that you can look into. We found though that a good balance between security and usability is to set this parameter to a value of 1. And this is going to allow you to do the time-based and the data access-based profiling. If you want to do other types of profiling, like branch prediction profiling, you should be able to access the specific counters. You just won't be able to access all 8 associated with their profile at the same time. Okay, the second stage is the translate stage. This is where we translate that profiling data into something that we can use. Again, we're going to use the Amd Uproof CLI bin command. In this case, instead of collect, we're going to use report, and then -i refers to the file that we're going to be then ingesting. In this case, it will be output using the name that we specified during the collect stage, .caprof. And again, it's going to generate two output files, output.csv, output.db, and these are going to be located in a new directory named output. And then finally, we're going to analyze the results. So profiling data can be analyzed anywhere. And I would say the preferred way of doing this would probably be to install the AMD UProf GUI on your local machine. But AMD does not currently have an implementation for Mac, and I'm a Mac user. So I'm stuck for now for working with the working with the plain text output. But if you have a Windows or a Linux box, you can install the UProf GUI. And in fact, if you go to my repo, you'll see that I do have the database files. So you can take those and you can import them to GUI and start experimenting. For now, though, I'm just taking the CSV output and I'm pasting it into Excel. And I find that this works pretty well. It just requires that you spend a little bit of time familiarizing yourself with the output. So we're now going to get into a profiling example. So I put together a toy code. It doesn't do anything useful. It consists of a main program that's then going to call two subroutines, sub1 and sub2. It's going to call that first subroutine twice, the second subroutine once. Those subroutines, in turn, are going to call functions f1 and f2, and they're going to do it n times, where n is going to be an input parameter. So to build my code, I'll build it just like any other executable. In this case, it's Fortran code. I'm going to use the Intel compiler, ifort-g. I'm going to specify the architecture. I'm going to use aggressive optimization, in this case, -03, which will allow the compiler to do things like function inlining. That's where it takes the body of a small function or subroutine and inserts it directly where it's called. That gives you a lot of performance advantages since you avoid the overhead of calling those functions or subroutines, and it also gives you opportunity for vectorization. So I'm going to build the application. Next, I'm going to use uprof to collect profile information. In this case, collect --config TVP for the time-based profiling. I'm going to specify an output file. I'm going to call it intro-tvp. You could call it anything you want. I figured in this case, this would be easy to remember since it's the name of my executable, followed by the type of profiling I'm doing. And now I'm just going to execute execute my binary the way I normally would, /intro. I'm going to pass a value of n of 1 billion. So I'm going to be working on arrays of size 1 billion. And then finally, the translate phase, where I'm going to take the output of the collect phase and generate something something a little more useful. Let me just check the chat. So there's a question here. How would you compare the uprof to Intel profiling tools, vTune and Advisor? You know, I'm not quite sure how they compare, but I think that vTune, I think that uprof actually allows you to go a little bit deeper. And there's a question here from Manu: which module loads the profiler? So it's a Manu. So we don't currently have uprof installed for general use. It's just installed on one node right now. So eventually we will have a module for that.
Thanks a lot.
And then finally, there's a question here. Is this part of the AMD compiler suite? So I believe that uprof is independent of the AMD compilers, because we have the compilers available on all of the nodes currently, and the uprof is a separate installation. And then finally, question from Alexander. Oops, sorry, lost that. What happens if some of the profiles counters are inaccessible? So all of the individual counters will be inaccessible. But if you try to use too many counters, if you exceed the number of allowed counters based on the paranoid setting, then it's just not going to run. It will give you an error message and stop. And then finally, see one last question here. Does uProf need access to the source code? No, it only needs access to the binary. But if you compile with -G, you'll then have the symbol information so that you can tie usage back to the source. All right, so moving on, just to illustrate my example, you see here on the left, I have a snippet of the main program. Shows that we're allocating several arrays, W, X, Y, and Z. We're then going to populate arrays X and Y. Here I just putting in some dummy values based on the loop index. Then I'm going to make 3 calls, 2 to sub1 and 1 call to sub2. Then when I look on the right panels, subroutine 1 and subroutine 2, all they're doing is executing a loop over the elements of those arrays and calling functions F1 and F2 element by element. And finally, it's in F1 and F2 where the real work is being done. And again, nothing useful, just doing some arithmetic and divisions. Okay, so when I look at the uProf CSV output, it's a little bit like drinking from the fire hose, but it is just plain text. At the top, you're going to have the execution environment and the profile details. This is nice because sometimes you might do a profiling and you forget what the parameters were, what the input arguments were, which hardware you were running on. So the top has all of that information. Next, we get into what they call the hot functions section. If you're familiar with gprof, you could think of this as just a listing of the functions ranked by the amount of time that they consume, and then followed by what we call a function details section that will dive into what's going on in each of those functions. So taking that output, cleaning up a little bit, this is what we see when you use uProf, time-based profiling, allowing the compiler to do inlining. If we look on the left, we'll see that there's just one recognizable routine that accounted for the time. In this case, it was main, and then it's followed by a bunch of system calls, clear page rep, do page fault, and so on. On the right, this is where we dive into what that function, in this case main, is doing. You'll see that the code, that the subroutines and the functions were actually inlined. So what we're seeing here is an assignment of time to the lines of the inline code. So of course, that this isn't quite going to correspond to your original code. In this case, it's pretty reasonable. We see that there's about 5 seconds that are assigned to F1, about 7 seconds that are assigned to F2, again, after inlining, and a little bit of time associated with other statements. Now, if I recompile the code, if I deliberately turn off inlining, then I'll see a breakdown of usage by the functions and subroutines. In the left panel, we'll see that F1 accounted for 32 seconds, F2 accounted for 18 seconds. You notice the runtime is a lot longer because we now have the function call overhead, and we weren't able to do the vectorization. We see a little bit of time is associated with sub1 and sub2. But if you look on the right, you'll see that uProf doesn't do a perfect job of assigning usage to statements. So in particular, for function F1, you'll see that the majority of the time is actually assigned to the end function statement. So I would say, when you're looking at the assignment of time to individual source code, individual lines of source code, there's something useful there, but I would take the results with a grain of salt. Let me take a look at the chat. Does uProf work with MPI? Yes, you can use uProf with MPI codes. Now, keep in mind though that uProf is not a tracing tool, say like Tau. I haven't used uProf yet with MPI applications, but I believe the output you're going to get is going to be more like gprof, where you're getting an individual profile for each process. And can uProf be used to profile Python code and other interpreted languages? I do not believe so. I looked through the documentation and I didn't see any mention of C or Fortran. But if anybody finds that it is usable for Python, I'd be interested. So sorry, moving on. I'm going to go over the next few slides pretty quickly, since we want to make sure that we have plenty of time for insight. But quick digression before we get into data access profiling. So although µProf can tell you which functions are taking the most time, it can't give you any insights into why a particular function is expensive. So for codes with a low computational intensity, this is where we're doing a relatively small amount of computation for each word of data that is operated upon. Performance is really going to depend on how well we manage data movement, specifically how we make use of cache. And uProf gives us access to this performance counters and allows us to go deeper. So again, memory-bound codes. These are codes where the rate at which data can be delivered to the CPU is the limiting factor. And our goal is going to be to apply cache level optimization so that the CPU is not starved for data. On the other hand, compute-bound codes, like the one that we had just worked with, it's the performance of the processor that is the limiting factor. Data can be delivered fast enough, but the processor can't keep up. In this case, our goal is going to be to reduce the amount of computation done on a piece of data. And in real codes, we'll often find a combination of compute and memory-bound kernels. So just touching briefly on the computer memory hierarchy, I think a lot of you have seen graphics like this before, where at the top, we have registers with very, very limited capacity, but data in register is available for immediate use by the CPU. Down at the bottom of the hierarchy, we have disk, hard disks, and SSDs, which are very, very far from the processor, but of course, much, much larger capacity. But what we're really interested in is the middle part of the hierarchy, the multiple levels of cache. You could think of this as very, very fast, small memory that's on the processor. That's much easier, much quicker to access than main memory or the DRAM. So what we want to do is get data moved into cache, and once it's there, we want to try to reuse it. So for cache, there are two things we need to keep in mind. There's temporal locality and spatial locality. Once we load data into cache, we want to make sure that data that was recently accessed is going to be used again. So the idea of temporal locality is once data is in cache, it's likely that you're going to use it again. Spatial locality means that if a piece of data is accessed, it's likely that neighboring data elements will also need to be accessed. So to take advantage of spatial locality, cache is organized into lines. Here I say typically, but in modern processors, I've never seen anything other than a 64-byte line. And an entire line is loaded at once. Let me take a quick look at the chat. So a question here from Halran Sun. Is it for Fortran only? No, it is for both C and Fortran. And Jeffrey commented here, C and Fortran and C++. Yes. And there's a comment there also on Python. And I'll just move on, and I'll let that conversation go on the side. Manu also asked, can we get NUMA-related cache stats? So Manu, I had gone through the uProf user guide in pretty good depth, and I did not see anything in there about NUMA-related cache stats, but I should go back and look again.
Yeah, but it'll be interesting because the current architecture has a lot of NUMA domains, so it'll be interesting to see if we can get some stats. Yeah, thanks.
Yep. Okay, so moving on. So I am almost out of time. I'm just going to go over this very quickly. But just going to touch on multi-dimensional arrays. So in one-dimensional arrays are laid out in memory in the order that the elements appear. Multi-dimensional arrays, there's no such thing as a multi-dimensional array in memory. Multi-dimensional arrays need to be laid out into a 1D array. And we have two conventions, column major order and row major order. So in column major order, and this is using Fortran R and MATLAB, the first or the leftmost index varies fastest. So if I look at this grid of look at this grid of the 16 values, we're going to go down the first column, second column, third column, fourth column. You'll see this layout 0, 4, 8, 12, 1, 5, 9, 13, and so on. Row major order is what we use in Python, Mathematica, and the C family of languages. Here we're going across the rows. So what this means is that when I'm working with multidimensional arrays, if I want to make good use of cache, if I want to access elements in the same order that they're stored in memory, I want to make sure my loop nesting is correct. So this is an example of adding two 2D arrays. In Fortran, I have do j, do I, and then zij equals xij plus yij. So this is the correct nesting for Fortran. And then below that, I have the correct nesting for C code. Notice that loop over I is on the outside. And the reason I bring this up is because in our next example, we're going to look at the performance of a matrix addition problem. And this is in the repo that I posted earlier. So here I measured the runtime for the addition of two large n by n matrices. And I saw some really surprising behavior. Here I ran it for 3 different problem sizes: 32,767, 768, and 769. When I used the proper loop nesting, as we would expect, the runtimes are all about the same. When I had the improper loop nesting, we're going to be making poor use of cache, and you would expect the code to run a lot slower. But look at that middle result in the last column. So for the first case, it took about 29 seconds, about 15 times longer. For the bottom case, it took 21 seconds, about 10 times longer. So already we're seeing a big variation. But for the case of 32,768, it took, what is that, about 60 times longer, and considerably longer than the slightly smaller or the slightly larger problem. So this is the case where data access profiling can give us a lot of insight. I don't need to do time-based profiling because it's just one routine and I already know where the time's being spent. But if I do data access profiling, maybe this will give us a little bit deeper understanding. So I'm going to build my code. I'm going to use the uProf to collect profile data, and then I'm going to translate. The key thing that's different here is that for my profile, instead of TBP, I'm using data access. And if I look in the function detail section of the report generated by uProf, particularly at the cache misses, look at the number of cache misses when I had proper loop nesting. It's around 10 to 11,000. Look when I had the improper loop nesting, though. You can see that instead of about 10,000 cache misses, for the first case, we had almost 200,000. In the third case, we had 116,000. And in that case, for 32,768, we had nearly a million cache misses. So about 100 times worse than when we had the proper loop nesting. So again, this is one of those things that we don't have time to get into much detail. But this tells me that I'm really making terrible use of cache. When I have that exactly wrong problem size, 32,768, I'm banging on the same cache lines over and over and over. So not only am I making terrible use of cache, but I'm banging on that same cache line and constantly pushing data out, and I'm getting terrible performance. And this was the kind of insight that we're able to get by using by using data access profiling. What's nice about this is you don't need access to the source code. You could have run this on the on a binary that you were provided with, and this will be really useful, especially if you see quirks in runtimes as a function of problem size. Let me just take a look at the chat real quick. So is the G flag required for profiling? No. Okay, thank you, Jeffrey, for answering that already. Yes, it's not absolutely required, but you'll get more information. Like I said, you'll have the symbol information if you compile with -G. And does AMD's uProf have any utility for at least AMD GPUs? Yeah, yes, it does. I haven't experimented with it. I think that I didn't have an opportunity to anyway because we have NVIDIA GPUs. But if you look at the user guide, it does have capabilities for AMD's Radeons. And then for cache misses highlighted in the report, what type of hints does the profiler offer to fix this? The profiler doesn't actually give you any hints. And the associativity of the cache, Richard, I'll get back to you while Mahidar is giving his presentation. I'll track that down. I'll post that into the chat.
Hey, Bob.
Yes.
Mary here. It's 11:30.
Oh, yes, I need to get going. Okay, I will wrap up here.
Great job.
Thanks. So where to go for help? Searching for You Prof or µProf. The AMD uses these two names interchangeably. So this drives us nuts. In fact, they do this even within the same web page or the same document sometimes. You could do Google searches using each, and they will get you to the official AMD documentation. But if you go a little bit further down, looking at, say, community input, you're going to get different results for µProf and uProf. I would suggest that if you're doing a search that you use both for now. And then finally, and I need to hand things off to Mahidar to talk about NSIGHT, there are some self-paced exercises that you could do. I'm going to suggest while we're waiting for the for uProf to be installed, that you take a look at the AMD user guide. And then I have some experiments that you can do here with both the matrix addition example, looking at different problem sizes, different compilers, and for the introductory example, that toy code, to look again at the effect of you using trig functions, log functions, and breaking the file into multiple files. So with that, I'm going to stop sharing, and I'm going to hand things off to Mahidar.
Thanks, Bob. So let me get my presentation going. So do I have the right one shared, or let me swap displays?
I think you need to swap them.
Yeah. All right. So
That looks good. Thanks.
that looks good, right? So what I'm going to talk about is basically profiling, GPU profiling on Expanse. Let's see if I can get my, yeah. And just a quick outline. So I'll take a look at the command line NVIProf option first, and look at the options and take some of the CUDA SDK examples to just illustrate how to use it, and do a quick OpenFCC example. And then look at NSIGHT systems, which will basically look at both the CPU and GPU profiling at the same time, both the CLI and GUI options. And again, we can go back and look at the same examples and see how to use it. I'll give a brief overview of NSIGHT Compute. It's currently disabled on Expanse for the same kind of security reasons that Bob was talking about. We have to figure out a way to make that happen. Probably what we're going to do is set a feature that will let us do this on an exclusive node so that some of the security concern is mitigated. But right now it's disabled. So starting off with the NVIProf, it's a command line tool that basically profiles CUDA related activities, both CPU and GPU. You can look at the results on console, or you can save them and then look at them later using NVIProf or using a visual profiler. Both of these command line options are, and both NVProf and NVP are going to get folded into, or the functionality is going to get folded into NSIGHT, and I think they'll get deprecated in a year or so. But right now they're available, and it's a nice, quick way of looking at things. In terms of what kind of options you have for CUDA, you can look at events, different kinds of metrics, kernels and memory, source level analysis, dependency analysis, and so on. And then for CPU, you can look at the basically OpenACC, OpenMP, scope, and so on. And I'll look at some of the options. And there are print and IO options related to, like, what level of summary and import export of profiles and so on. There's a long list of options. So if you want to look at the details, you should go to the link that's out there. So the first thing I wanted to look at was basically just how do you find out what kind of metrics or events you can look at. So NVIPROF -- query metrics will give you a long list, and similar thing with query events. I just have a snapshot of it, of the first few. There's probably 100 plus in each of them. And you can see the kinds of things you can look at: instructions per warp, branch efficiency, warp execution efficiency, and so on. So there's a lot of different things you can do. I see a question about a Git or a link for NVProf. I will get these uploaded once the talk is done. So simplest thing you can do is just run it with no options. So basically run NVProf. In this case, I looked at the matrix multiplication example, and you can see there is output that's corresponding to what the code is putting out. So it's telling you what kind of GPU device it is, and it's doing the matrix multiplication and some performance info. This is all not from the profiler. You'll see underneath it says profiling application result. That's where the profiling output starts, and you can basically see the time percentage, the time it's taken, number of calls, average, min, max, and the name of the call. So you can actually get a quick look at what's going on in the code. And if you want to try these out on Expanse, you can copy over the CUDA toolkit examples and build them and test them out. And it's quite straightforward. If you load the CUDA toolkit and the CUDA profiler modules and run make in these simple examples directories, you should be able to get the binaries and then test things out. So looking at the kinds of things you can do. So first thing is, if you want to do interactive tests, you can get interactive access using srun. That's a command that's showing you how to get it for 15 minutes on one GPU in a shared GPU shared partition. You can of course change these limits, and the only thing you really need to put specific to your account is the allocation ID. And then notice I do a module reset that basically resets the modules to the system defaults on the GPU partition. And it's different on the GPU and CPU. Our stack on Expanse is different on the GPU and CPU. So once you're done with the setup, you essentially are ready to go test. So one simple thing you can do is beyond what we did in the first slide was basically do a GPU trace. And this will give you a timeline of activities on the GPU in chronological order. And similarly, you can do an API trace, which will show you the API invocation on the host in chronological order. You can also collect info on selected events. So remember, we had the options to figure out what kind of events you can look at. And you can do NVProf with the -- events and the -- metrics. They can be used together and for asking for specific things. Now this last one again needs permissions to be set up, and again we are working on this. This will be the thing enabled with the feature. So what does an output look like? So this is just sample out from the GPU trace. So you can see that there is a start and end, and start and duration, and it's basically a chronological order of what's going on. There's a lot of host to device copies in this case in the beginning, but you can basically look at the output there. You can also do a system profiling option. So what that does is gives you a little bit more info on what's happening on the GPU at the system level. So like low frequency sampling of the power, the clock, and the thermal behavior. This is it's good to have this info because sometimes if the codes are really efficient, they might trigger like they might start hitting the limits of either the power or the clock. It shouldn't, but we have seen that happen on Comet a few times, and it's been we have to go back and look at the node to see if there's something needs to be fixed, or like say a slow fan speed or something that might cause things to heat up and hit the limits. So it's good to get that kind of information to see if your run was slow because your code's got a problem or if there's something else going on at the system level. So you can run that with the system profiling on option, and I have a snapshot later. And then for OpenACC, there are options. You can run it directly without any options, and it'll give you some level of info. You can also get an OpenACC trace. The last thing I want to talk about with the NVIProf is that you can actually export the profile and then open it in a different, like with NVPP, for example. And I have some snapshots of that. So if you look at the system profiling on option, then you can see you still have that info that we had about the memory copies going on and everything, but then you get info on what the GPU is doing at the low level. So you can see the temperature is 40 and the power is well under the limit and so on. So you can get a sense of whether you're hitting throttling for some reason. And like I said, you could take the profile from the NVProf, export it, and then read it in on an VP, the visual profiler, and get a little bit more readable and kind of visual look at all the events. But all that to kind of move into NSIGHT. So NSIGHT systems is basically system-wide performance tool, and it can again combine info from both the CPU and GPU. The nice thing is it's a full system view, so you can identify bottlenecks at different levels. So like say you have a GPU starvation, or you have too much synchronization overhead, or you have some issue on the CPU side where you're not parallelizing enough, or you have some data movement inefficiencies. This again can be run both in CLI and graphical mode. When you run in CLI, you can basically export the report files and then you can view them on a client machine. And that is what I would recommend, just like Bob was talking about reading the You Prof profiles on your own machine. It's good to do the same for NSIGHT, because you can technically run X forwarding and get to open the GUI from Expanse, but it's going to be really slow. So the better thing would be to run it, export the profile, and then read that on your own machine. And there are lots of tracing options, different CUDA libraries. You can look at OpenACC, OpenMP, OS runtime stuff, and MPI. And MPI, basically, there are OpenMPI and MPitch options. And since both Intel MPI and VAPitch are based on MPitch, I would expect it to work for them too. And the CUDA and OS runtime backtrace options are also available. Again, there's a lot of options, and you can actually look at the user guide for that. Now, how do I use this on Expanse? Again, you can set up interactive access like before, do the reset, just load the CUDA toolkit, And right now I have NSIGHT in a different path because I had to install a newer version to get around some bug. But there will be a module for this very soon. And pretty much then you do NSYS profile with whatever options you want. Like in this case, we're looking for CUDA and OS runtime. And we're just outputting it to a baseline profile and then writing out output and running basically one of the examples. So if you look at how this will play out on the command line, you'll see the output from the code. And then at the end, you'll see this saving temporary file. And then it actually processes that file and creates this report file that you can download and read from your client locally. So that's what I did. I basically copied this over. And then when you look into the profiling, so when you open it up, you'll see there's the OS runtime stuff, there's the CUDA API, there are all the stream, all the stuff happening on the CUDA hardware. And you can see there's a lot of setup in this kind of this example, and the actual compute is this tiny piece on the left, on the right, sorry. So what I did is zoomed into that. And that's the nice thing with that. You can drill down and look for particular routines. And actually, if you mouse over, you will get summary information on that particular routine. And you can see on the right the kernels, the percentages for each of the kernels there. And then you can drill down into each of these things. Just for comparison, I did the same thing using NVIProf, and you can see the same routines are showing up. So that's kind of consistent. At least that's nothing different. So yeah, I'm going through real quick because there's a lot of things to cover, but there's all these sample codes are on the machine, and if you follow through with the commands that I had, you should be able to play around and get some info yourself. So one thing I wanted to show is like, how can I use NSIGHT systems to kind of get some insight, right? So this is a good example from NVIDIA where they have a sample code that uses unified memory data movement and does a memory addition. So what the example does is look at the two approaches for this data movement, with and without prefetch, and you can see at how that looks on the profiles. So like if you run it without prefetch, you can see that there's a lot of data transfer going on and the compute at the same time. So this is not going to, there's going to be a lot of delays because basically you're moving data around during the compute. And if you look at the same, and this is a zoomed in thing where I zoomed into the piece that is doing the actual compute. But if you go look at a prefetch option, then you'll see a bunch of data got prefetched, and then there is a small compute at the end. So you didn't overlap those two. So you can visually see that in the profile. So if you're looking, I mean, this is a very simplistic example, but if you're looking at a complicated code and you see pieces that look like they're blocking each other, like say there's a huge memory transfer that's blocking everything till that finishes, you can always make an optimization and see if it changes things, right? So so this was a good example that you can quickly run and look at it. Then the last thing I wanted to talk about was the NSIGHT compute. So actually one thing I wanted to say is, like, if you go back here and if you, let me see. So in this plot, if you actually click on that and you say you feel like that particular routine is not efficient, or you want to look at that in more detail, if you click on that, it'll actually give you the command to profile that particular piece using NSIGHT compute. And then you can go back and look at the kernel in much more detail. So that's what the NSIGHT compute lets you do is like it's an interactive kernel profiler, and you can look at things in depth for CUDA applications. It's part of the CUDA toolkit. And both the GUI and the command line options are available for this. Again, the features are like you can compare performance metrics between baselines on a current run and in the same interface. So that can give you a very quick look at what changed if you're making tuning changes and things like that. You can actually look at basically you can do CUDA task graph profiling. You can look at source code correlation. There's also a roofline analysis, kind of lets you know how much headroom there is to even optimize and what the possible limits are. Again, this is currently disabled, but we'll probably get at least like a single user on a node feature setup so that we can enable this. There is a really nice blog post, actually 3-part series where there's analysis-driven optimization kind of analysis shown. I see a question, is there any information that NVIProf provides that's not available via NSIGHT? Not really. You have the same restrictions. So like, remember like the metrics that I was talking about up there, those are really what are the lower level ones, right? Go back here. Yeah, this piece here is not going to work right now for you, the NVProf -- events and the -- metrics. And this is where you really get the like in-depth info, and actually you can profile particular pieces and all those kinds of things. I mean, the NSIGHT tools essentially make it a lot easier for you to do it, but you're doing almost the same thing at the lower level. So the restrictions going to be the same, unfortunately. So, but you can look at that link that I have to see the kinds of things you can do, and hopefully we'll get this enabled soon. For now, I think the NSIGHT systems piece is what is really working, and like you should be able to get most of the info that you need from there. You should be able to identify problems. So what does it? CUDA profile. Actually, I don't know what the difference is. Is there a separate? I've never used that. I've actually used NProf most of the time. So I'll have to check on that and get back to you. So those are the kinds of things you can do. So far you can look at. So just to summarize, there are command line and GUI options. Right now we have permissions restrictions, so that's disabling some of the features. So if you want to do something quick, I would say use NVProf. And there are several options to profile just the GPU piece or the CPU piece, API calls, and so on. And there's a dependency check you can do, and all sorts of options even at the command line. And you can easily profile OpenACC codes using this. If you have NSIGHT systems client installed on your desktop or your laptop, and you run the NSIGHT systems profile using the CLI option and write out the report, that's probably the best way to use the systems. And for that, there is a Mac client that works fine. I had a problem with the Mac client for NSIGHT compute, so I have to try it out. I have a pretty old Mac, so maybe I'm just resource starved, but I have to actually look at what's going on there. But there are client tools that you can download for both of these packages, as long as you're signed up as an NVIDIA developer, I think, which you should be able to do if you're developing code. There's no issues doing that. Quite straightforward. I think I'll stop at that and see if there are any other questions, or if Bob has anything else to add. I think he was going to check on something, so you have a few minutes. All right, so I think we're good. So as I said, these examples are basically on Expanse, and you can copy, and I'll get the slides up as soon as we are done.
And yes, I'll get the recording up as soon as possible too, and I'll send a link to all of the registrants to the recording.
There's a question about, are there any differences when using NSIGHT for Julia? I have not done that actually, so maybe something I can explore and get back to you.
Okay, great. Well, thanks very much, Mahidar and Bob. Great presentation. And everyone, thanks for joining. Have a great rest of your day.
Thanks, everybody.
Great, thanks everyone.
Thanks, Mahi and Bob.